later. The next lesson is key value store. The next talk really is key value store. Okay, thank you. Hello everyone. Welcome to the engineering, product, and TPM talks. A special welcome to engineering leaders and TPM talkers, builders, and doers. This is the fourth part of a 16-part series devoted to system design building blocks. I've said system design problems usually have some similarities, though individual solutions or specific details will be unique. And in the system design building block series, we want to look at those elements of the building blocks that are similar across design problems. Already in this series, we've looked at DNS, domain name systems. We've looked at databases. We've looked at, So one example of a building block is a database, which enables us to store, retrieve, modify, and delete data. But another common system component is the key value store, which is a non-relational database that stores data in the form of a key value pair. Now, I'll try to make this a little bit fast and a bit superficial on the surface, because if you want more detail, you can look at the previous talk on databases. But here, what I'll try to do is I'll try to explain the design of a key value store along with important concepts such as achieving scalability, durability, and configurability. Don't forget to like and subscribe. Let me know. Okay, we like to start with a thought that may or may not be related to the discussion at hand. Today's thought of the day is from Rabindranath Tagore, who says, "The truth comes as a conqueror only because we have lost the art of receiving it as a guest." That is, the truth comes as a conqueror only because you have lost the art of receiving it as a guest. For me, this tells me that I need to be more open to feedback, whether positive or negative. So please give me all your feedback in the comments. I'm happy to receive them. I'm happy to learn. Importantly, particularly for engineering leaders and TPMs, do not be afraid to receive feedback yourself. Always start with your customer and work backwards. Who is this for? It's for technical program managers, product TPM, system engineering leads, anyone that's really involved in the digital tech system. This is for you. Thank me later. We've covered domain name systems, load balancers, and databases. This is key value store. But we're also going to cover the remaining blocks, right? These are the 16 different building blocks or Lego, I believe, are relevant to the system design. As I've explained, some of my motivation is the fact that the UK is facing a shortage of skilled workers, and I'm hoping that these talks, although this is not primarily devoted to the UK, but in any country, anywhere, anyone that needs to brush up their tech skills, tech knowledge, understand what the basic building blocks are, this is for you. Okay, so what is a key value store, right? Key value stores are distributed hash tables, DHTs, where a key is generated by the hash function, and that key should be unique. In a key value store, a key binds to a specific value and doesn't assume anything about the structure of that value. A value could be a blob, an image, a server name, or anything that the user wants to store against a unique key. Usually, it's preferred to keep the size of a value relatively small, say kilobytes to megabytes, but we can also put large data, because we can put large data in large data in key value stores, but typically you'd expect to put that in a blob storage, and I'll cover that as one of the building blocks. Now, it's challenging to scale traditional databases with strong consistency and high availability in a distributed environment. Many real-world services like Amazon, Facebook, Instagram, Netflix, and use primary key access to a data store instead of traditional online transaction processing, OLTP, online transaction processing databases. So example of key value storage include best-selling lists, shopping carts. Yes, you didn't know, did you? Customer preferences, session management, sales, product catalogs, etc. And now many applications that do not require a rich programming model, that's the kind of rich programming model that will be provided by an RDBMS, Relational Database Management System, would benefit from a key value store. Why? Well, because key value stores provide configurable services, right? So sometimes it's difficult to scale traditional databases with strong consistency. So in that situation, a key value store would help. How does a key value store look like? Essentially, you have a key, you have a value, and you have a store. And typically, they benefit from reliability, scalability, and availability, right? So what are sort of functional requirements that you'd expect to see from a key value store? Let's say you're trying to build one from scratch. Typically, you want it to be configurable, so you want to see strong consistency to be traded for high availability. You want it to be always able to write. Now, just to be clear, write availability is typically seen as a non-functional requirement. Okay. However, for our notes, for this specific example key value store, is actually seen as a functional requirement. And this is because the ability to always be able to write, that's high availability in terms of write, is a functional requirement for, think of Amazon shopping cart application, right? So while in other cases, high availability may be considered a non-functional requirement, when it is the reason for the design, then it becomes a functional requirement. So if you consider Amazon Dynamo Key Value Store, that's DynamoDB Key Value Store, you can categorize the ability to write as a key functional requirement. Yep. Another functional requirement will be hardware heterogeneity. What that means simply is that you want to be able to add new servers with different capacities, higher capacities, seamlessly to the cluster without changing or upgrading existing servers. So the system should be able to accommodate and leverage these different capacity servers, ensuring correct core functionality, get and put data, while balancing the workload distribution according to each server's capacity. What are the non-functional requirements that we consider? I would say scalability, right? We want to be able to add or remove servers as when needed with minimal to no disruption. Fault tolerance, you want to be able to operate you want your key value store to be able to operate uninterrupted with minimal disruption to service or the components. So just to summarize, key value stores simplify the storage model by focusing specifically on the key to value mapping, eliminating the need for complex programming models of the traditional RDBMS. They excel in those environments that demand high performance, especially for write operations, and can efficiently operate across diverse hardware configurations. The flexibility and performance efficiency make them suitable for scenarios where rapid access, essentially write data, is critical, and the data model does not require the relational integrity and query capabilities of an RDBMS. So essentially, cut down RDBMS when you need key value store. So how are we going to design the key value store, right? So let's assume, first of all, some assumptions in terms of API design. First, we will assume that the data centers hosting the service are trusted, non-hostile, just to simplify the design. We will assume that all the required authentication and authorization are already completed, because that introduces elements, API gateways, etc. We'll also assume that user requests and responses are related by HTTPS, because the other things we could use a WebRTC, we can use gRTPC, there are other methods. Okay, so if we assume that, then we can say that for the get function, the API call to get a value will just look like this: get key. That's simple. And what we return is, we return the associated value on the basis of the parameter key. That's it. Okay. So when data is replicated, it locates the object replica associated with a specific key, and that is typically hidden from the end user. And then this is done by the system and store. And if the store is configured with a weaker data consistency model, for example, in eventual consistency, there might be more than one value returned against the key, but ultimately it will be normalized to that one value. For the put function, right, this is essentially is the key against which we want to get value. So the put function, the API call to put value into the system should look like this: put key value, where the description is the value is the object to be stored against the key, right? So the key is often a primary key in a key value store, while the value could be any arbitrary data, whatever we store, right? We mentioned some of the types of things that we want to store. Note something like DynamoDB uses a MD5 hash on the key to generate a 128-bit identifier just for security. These identifiers also help the system determine which server node will be responsible for that specific key. The data type key is often the primary key in the key value store. Value can be any arbitrary data. Get and put data while balancing workload distribution according to the server's capacity. So the key value store has to be scalable. So key value data is stored in storage nodes. With a change in demand, we might need to add or remove storage nodes. It means we need to partition data over the nodes in the system to distribute the load across all nodes. For example, let's consider that we have 4 nodes and we want 25%. We have 4 nodes, node 0, 1, 2, 3. That's 4 nodes. And we want 25% of the requests to go to each node to balance the load equally. The traditional way to solve this is through the modulus operator. Each request that arrives has a key associated with it. And then when a request comes in, we calculate that. So when a request comes in, we calculate the hash of the key, right? So this is the modulus operator here, M, modulus. And then we calculate the hash of the key. And then we find the remainder by taking the modulus of the hashed value with the number of nodes. The remainder value X, this is X, the remainder value X is the node that we go to, right? So if we want to add and remove nodes with minimal change in our infrastructure, we need some kind of way to do this. Okay, so this is fine for a 4-node set. Imagine if we have hundreds of nodes. What do we do in that situation? That's one. But 2, if we want to bring nodes in and remove nodes, how do we do that? It's going to be inefficient if we use this kind of system. For example, if node 2 is removed, and suppose for the same key, the new server to process the request will be node 1, because 10 modulus 3 will be 1. Now nodes will hold information in the local caches, like keys and their values. So we need to move that request data to the next node that has to process the data. Again, so this processing in between the nodes is what's going to cause the complications. So one thing we can do is we can use virtual nodes, right? So with virtual nodes, they can ensure more evenly distributed load across the nodes. Because instead of applying a single hash function, we apply multiple hand functions onto the same key because they're virtual, so we can do what we like. So suppose we have 3 hash functions, just a thought experiment, and for each node we calculate 3 hashes, yeah, and place them into a ring. For the request, we only use 1 hash function. Okay, so just like in databases, we have to replicate data. Tell me if you can still remember why we do that. We also have to replicate that for key value stores. Okay, there are multiple ways of doing this. One way is this works, primary, secondary, peer-to-peer approach, right? Where one of the storage areas is primary and other storage areas are secondary. The secondary will replicate its data from the primary. The primary will serve the write request to the primary will serve the write request while the secondary serves read request. The primary serves write request, secondary serves read request. Then after writing, there's a lag for replication, obviously going forward and backward over the network. Moreover, even if the primary goes down, we can't write into the storage. So that becomes a challenge and it becomes a single point of failure. Um, that's an example of primary. Then in terms of peer-to-peer approach, all involved storage areas are primary and they replay the data to stay updated. Both read and write are allowed on all nodes. Usually, again, this will be inefficient, especially if you want to scale and costly to replicate in all n nodes. Instead, 3 or 5 is a common choice for the number of storage nodes to be replicated. Yeah. So let's consider an example replication. Okay, let's say we want to replicate data on multiple hosts to achieve durability and availability. Say the replication factor n is set to 3. Then if we choose n to be 5, it means we want our data to be replicated to 5 nodes. If we choose it to be 3, we want it to be replicated to 3 nodes. Each node will replicate its data to other nodes. We'll call a node coordinator, right? So we'll call a node coordinator that handles read or write operations. It's directly responsible. Where has that gone to? Yes, we'll call a node operator. We'll call a node coordinator that handles read or write operations. Is directly responsible for the keys. So the node coordinator will be directly responsible for the keys. And then a coordinator node will be assigned to be the key K, right? So this is a coordinator node. A this is the key K. And then its key K will be processed by node B. Key L will be processed by node C. And like that. Yeah. Now, in the context of the CAP theorem, key value stores can either be consistent or available, but not both when there's a network partition. So for key value stores, we typically prefer availability over consistency, which means if 2 storage nodes lose their connection for replication, they will keep on handling the request sent to them. And when the connection is restored, they can sync up. But in the disconnected phase, it's highly possible for the nodes to be inconsistent. So we need to resolve such conflicts. Okay, so how do we resolve such conflicts? And this just brings you up to what I've just said. Yeah, we prefer consistency, we prefer availability over consistency. Okay, so how do we bring them up to speed? Data versioning. That's the answer, right? So when network partitions, right, and node failure occurs, then during an update, the object's version history might become fragmented, right? As a result, it requires a reconciliation effort on the part of the system. It's necessary in this sense so see here, 2 nodes are replicating their data while handling requests. All is fine, all is going well, all is hunky-dory. But if we want to handle inconsistency, we need to maintain causality between the events. So the ways we can do is we can use timestamps that tells you when the last request process occurred, and then you update accordingly. Or, but the problem with using a timestamp is that if you use a timestamp, it's for a distributed system, think of geographically dispersed system across the world. The timestamp will not necessarily be accurate. It could be out of sync, even if by hundreds of a millisecond. That's bad enough, right? So we can't use that as a deciding factor. Another approach is to maintain causality. So now the network connection between the two nodes breaks. So that's the network partition has happened. That's what we're talking about now. So we talked about trying to use timestamp to solve this. We said, what about, because the nodes will continue to handle the request, right? Even though there's a break in the network partition. So we have to choose consistency or availability. You can't have both. So you said timestamps will not work because for a distributed system, it's not reliable to the degree necessary to make an education based on timestamp. So another option is a vector clock, where you have a list of node counter pairs, and then for each version of the object, you use the vector clock. So if two objects have different vector clocks, we can tell whether they are causally related or not. And unless one of the two nodes is reconciled, then they are deemed at odds, right? So when the connection is restored, the data in both nodes isn't necessarily the same. You need to resolve that. Yeah. So versioning, the function will find node that, so the function finds that the node where the value should be placed on the basis of the key and stores the value associated with it. The context will be returned by the system after the get operation. If we have a list of objects in context, then if we have a list of objects in context that raises a conflict, then we can ask the client to resolve it. Yeah. So this process of resolving conflicts is similar to how it's done in GitHub. Anyone that's heard about GitHub, which is a version control system for source code management. So Git is able to merge multiple versions into one. When Git is able to do that, it's done automatically. However, in situations where it is unable to do that, then it's up to the client, or think in this case, the developer, to resolve conflicts manually if automatic conflict resolution is not possible. So in much the same way as Git, our system can try automatic conflict resolution based on vector clocks, based on timestamp. But if that's not possible, then the application or the client can provide final result value. So in summary, a key value store provides flexibility and allows us to scale the applications that have unstructured data. Web applications can use those key value stores to store information about a user session and preferences. Then when using a user key, all the data is accessible, and key value stores are ideal for rapid reads and write operations. Right. So key value stores can be used to power in real time or recommendations and advertising, because the stores can swiftly access and present fresh recommendations. So data vision, I'm just saying here that you need to build in a way that explicitly accepts the potential of several copies of the same data so that we can avoid the loss of any updates. We need to realize that some failure scenarios can lead to multiple copies of data in the same system, and we need to resolve the conflicts among those divergent histories for consistency purposes. We said we can use timestamps, we can use vector clocks, yeah, provide context. Okay, so this brings us to the end of the key value store, which I which is one of the 16 building blocks for technical systems. If you have any question, let me know below. If there's anything that was not clear, let me know. Please don't forget to like, subscribe below. In the next session, I'll pick up from content delivery networks. So that's here. Okay. Thank you very much. Goodbye.